The weather is great here today, and spring is in the air. But with Britain's changeable climate, there's always a chance of a storm. Now imagine the perfect storm. One so powerful that it damages our power grids, takes out our communications, and renders our navigation systems useless. In this modern world, how would we cope? But this kind of storm isn't produced down here on Earth. These tempests are generated by the sun. Over to Sophia Herod from our Space Weather Centre for the latest update.
Thanks, Maggie. Hello. Well, we're in for some strong gusts over the next few weeks as high-energy particles stream out from the sun. But as we leave the solar maximum, we should see fewer solar flares and coronal mass ejections moving forward into the next few years. As calmer, milder conditions prevail, unfortunately, we'll also see fewer spectacular northern lights. But there's always a chance of a freak solar storm, sending huge fronts of plasma hurtling towards us. This could be hazardous to satellites and astronauts and could seriously damage our power grids. Back to you, Maggie.
Thanks, Sophia. Well, tonight we'll be finding out what space weather is and how it poses a danger to all of us. But we'll also be discovering how cutting-edge science is leading the way for us to build up resilience against the worst of its effects. Welcome to the Sky at Night.
Solar storms sound like the plot of a disaster movie. Billions of tons of plasma moving towards us at millions of kilometers an hour. But they're not uncommon. They are a fact of life for those of us living within the heliosphere, the vast bubble blown by the sun's solar wind, which protects us from interstellar radiation. But just occasionally, the sun demonstrates its might with vast storms that smash into our planet and which could wreak havoc for our technologically dependent society. I'm here at the Royal Astronomical Society to meet its president, Professor Jim Wild, a leading authority on space weather. He knows all about the last of these superstorms and the man who witnessed it. Thank you for having us here at the RAS, but why are we here?
We're here today to meet this chap, Richard Carrington. It was 200 years ago this year that he was born.
What's he famous for? What was he observing?
So Richard Carrington was a really talented astronomer. He was absolutely obsessed by the sun. And on the 1st of September in 1859, he was observing this amazing sunspot group, many times the size of the Earth.
And he obviously wasn't looking through a telescope. That's not safe. So what exactly was he doing?
So Carrington had set himself up with equipment so he could project an image of the sun onto a screen rather than observing it directly. So as Carrington was observing and making his sketches, he realised the sun's light was suddenly brightening. So he's the first person to ever, in recorded history, observe a white light solar flare in real time.
So he saw this brightening. Was that all that was happening?
Well, the flare subsided pretty quickly. Now, what Carrington didn't know at the time, and couldn't have known, that the flare accompanied a coronal mass ejection.
Coronal mass ejections are violent eruptions from the sun's churning surface that hurl huge clouds of plasma into space. Their origins lie in the twisting of the sun's powerful magnetic field, which forms giant loops as the sun rotates. As these loops snap, they release bursts of radiation, solar flares, and material can be thrown out. Along with a steady flow of charged particles called the solar wind, these events are what cause space weather. And back in 1859, Carrington had witnessed the start of a serious storm.
About 17 hours after Carrington observed the solar flare, an enormous geomagnetic disturbance started at the Earth. And this was mainly reported in people seeing the northern lights, the aurora borealis. Normally you'd see them at the edge of the Arctic Circle, but we have contemporary records of ships' captains in the Caribbean reporting them.
It wasn't just the northern lights that we're seeing, there are other effects as well.
The telegraph system was interrupted. So this is the Victorian internet, and telegraph sets spanning continents with copper wires had electrical currents induced in those wires.
Just by the influx of particles?
Well, it was due to the particles triggering electrical currents in the upper atmosphere, and those get induced then in the copper lines. Telegraph operators were able to use their sets even though they were disconnected from their power supplies. And some operators were actually electrocuted and telegraph stations set fire to. So this was the first sign that actually space weather, as we now call it, could have an impact on our technology.
So was Carrington recognised for this observation at the time?
Well, at the time, this was really cutting edge and pretty controversial. It was not understood how an effect on the sun could have this huge impact on the Earth. It was only much later that this was really understood, and we now refer to this as the Carrington event.
I like that it's got capitals, the Carrington event. Gives him a bit of credit. So what would happen if something the scale of the Carrington event hit us today?
If we fast forward to today, obviously we're a very technologically dependent society. So a lot of the technologies we rely upon, for example, radio communications, power distribution, spacecraft operations, those are all sensitive to some of the geomagnetic and radiation effects.
With satellite systems crippled and power grids pushed beyond their limits, the consequences would be immediate and severe. GPS could fail, global communications collapse, and internet access vanish, with vast regions plunged into darkness. One study estimated that a Carrington-class solar storm hitting the US would cause trillions of dollars worth of damage.
So how seriously is this taken?
So it may surprise you to know that extreme space weather is actually on the UK government's national risk register, alongside things like cold weather, flooding, all these extreme heat waves. It's a natural hazard that we should be thinking about. And so if you think of an analogy such as the Indian Ocean tsunami, perhaps in the days, weeks and months before that, it wasn't really an imperative to have all the warning systems in place and practice what you should do if one happens. Whereas the days afterwards, it seemed an obvious question to ask why you didn't do something about it. So responsible governments have things like this on a risk register, and scientists like me end up trying to work out what is the reasonable worst case scenario and how do we plan and mitigate against it.
But what sort of thing can we do to prevent our telegraph systems being fried?
So in the modern world, what you'd be able to do is set up your systems and your infrastructure to be a bit more resilient. It's really about putting our systems on standby, just as you would for a winter storm coming in from the Atlantic. You just start to plan and prepare.
How likely is it that we'll get a Carrington event in the near future?
Well, the statistics suggest that the scale of the Carrington event, that kind of event would on average occur once every couple of 100 years. And obviously the last time we saw one was a couple of 100 years ago. So maybe there could be one soon, but statistics don't really work that way, and we just have to wait and see.
So is a Carrington scale event as big as it gets, or is the sun more threatening?
Just like anything, a flood, a tidal wave, a volcanic eruption, there's a distribution of events. And Carrington is probably at the tail of one of the larger scale events. But there could be a bigger one on the horizon, and we've just not seen one yet.
Mounting evidence points to the disturbing possibility of larger solar storms. Data from isotopes locked away in tree rings and ice cores reveals sudden spikes in high-energy particles produced in the sun, 9 in the last 15,000 years. Known as Miyake events, at least 10 times more powerful than the one Carrington witnessed, they have a destructive potential that we barely understand. Across the globe, scientists are working on the mystery of how the sun's energy interacts with our planet.
To better forecast these extreme solar events, we need to get a better understanding of their interaction with the near-Earth environment. It reminds me of that philosophical question. If a tree falls in the woods and no one is around, does it make a sound? Well, it's just like that with space weather. Only when solar storms collide with our atmosphere do they actually become space weather that we experience. Dr. Ravi Desai from the University of Warwick studies what happens when particles from the sun crash into the Earth. So we have charged particles and plasma coming off the sun in all directions, but some of these travel through the solar system and hit our planet. What happens next?
It's an absolutely fascinating interaction between this plasma and our magnetosphere. Our planet has a molten core which generates a magnetic field, and it actually forms a sort of protective bubble around our planet. This means that when plasma comes from the sun, it can't directly penetrate through this magnetic field. However, this energy gets diverted. It strikes the magnetic field and it gets diverted into the poles of the planets.
Our magnetosphere is a vast magnetic field stretching far out into space. On one side, it is relentlessly compressed by the solar wind. Where it comes into contact with our planet at the poles, it forms funnel-shaped openings where high-energy particles from the sun can penetrate into our atmosphere. We were talking about sort of a protective element, but you're also saying that it guides these particles down towards the Earth. Is that a problem?
We can see the fact that Mars lost its atmosphere early in its evolution, at the same time that the planetary dynamo cooled down and it's lost its global magnetic field. So it could well be that our magnetic field protected our planet and it's key in sustaining life.
Yes.
But it's also important to note that this magnetic field captures energy coming from the sun. So it may not be as protective as we first thought.
Some of this energy forms the Van Allen radiation belts, zones of high-energy particles trapped by the Earth's magnetic field. Fed by the solar wind and supercharged during solar storms, inside the field, radiation levels can vary wildly.
And this was something that was discovered during the beginning of the space age when people launched satellites out into space and they suddenly discovered these swaths of energetic particle encompassing our planet, which form a primary hazard for satellites and astronauts.
As a space scientist in the past, I've built satellites, and we're trying to protect the satellites from these charged particles. But can you give an overview of what the charged particles can do to a satellite?
They can change the bits inside the memory of the satellite. They can flip zeros to ones.
Oh, so changing the data?
Yeah, which means the satellites will actually do something different to what you will actually expect. Charge can build up, and then you get arcing and breakdown of this charging, which can be catastrophic for satellites.
And that's not all. Solar storms funnel energy into the upper atmosphere, heating it up and making it expand. This can push dense air out to the edge of space. And suddenly, satellites experience drag they weren't designed for. Orbits decay, collisions become more likely. Some satellites fall back to Earth. In 2022, Starlink lost 38 satellites in a single event. We can see our magnetosphere as a beneficial thing, but it does cause some challenges of its own.
So we need to understand its response over short timescales so that we can forecast space weather.
So further investigation needed.
Definitely.
And so what sort of data can you get now?
You could say that space weather forecasting is about 50 years behind terrestrial weather forecasting. In space, it's much more difficult. We have fewer data points, and we're still trying to understand the fundamental physics of how the Sun-Earth interaction happens.
But work like Ravi's might be the key to unlocking the next generation of space weather forecasting capabilities.
We're developing forecasting tools to help predict and understand the dangers of space weather. One of these tools is called Gorgon, and this is a model which has been applied in many contexts, but we're actually transferring this to the Met Office. So if I hit play here, what you can see here is the magnetic field lines stretching out from the Earth out into space. And you can see here, as a solar storm impacts the Earth, these particles, they're trapped by the magnetic field lines. You can see the colors of these particles change, which represents the energies. And you're getting these vastly increases energies. And this means the dangers and the hazards are significant. So during these periods, we would want to be able to forecast what the radiation levels are.
So it's lovely seeing sort of the results from Gorgon here, but can it operate in real time?
A lot of effort has gone to be able to develop this model to run in real time, which means it can provide nowcasts so that satellite operators can understand what's happening right now. Ideally, you'd want to forecast these things several days in advance, but until we get better at observing the sun, and we won't be able to do that.
Hopefully, space weather prediction will be able to catch up with local weather prediction. And for that, more data.
More data, more missions, and more models.
Tools like Gorgon could be the next leap forward in predicting space weather. And Sophia Herod is finding out how. She's usually presenting the daily forecast, but today she's at the Met Office in Exeter, exploring a very different kind of weather.
Space weather is one of the highest priorities on the National Risk Register, the government's list for the most serious threats facing the UK, and the Met Office is playing a central role in the response strategy. I have to say, as an environmental scientist, it's absolutely thrilling to be here at the Met Office and getting to look inside a very special department. Krista Hammond is the manager at the Met Office Space Weather Operations Centre. Can you tell me about what you do here?
We're one of just a handful of centres around the world who are staffed 24/7, observing the sun, looking for signs of activity which can impact us here on Earth. It's important to note that like meteorology, like the weather we experience on Earth, space weather is occurring all the time with little impact. What we're looking for is the bigger events.
So when there's going to be an extreme space weather event, how much warning can you give?
I always think like the scale when we're talking about space weather is incredible. A slow coronal mass ejection can be going at 600-700 kilometres per second. The fastest CMEs will be here within about 15-16 hours. By the time we've done a bit of analysis to work out whether it's coming this way, plugged it into our computer models, you're looking at least 12 hours notice before a significant space weather event hits the Earth.
Who do you tell and where does all your forecasts go?
We're a member of the National Space Operations Centre, NSPOC. That's a joint military and civil initiative. So we'll be providing forecasts for them, the government, for different sectors like aviation, energy, so that they can be better informed about the potential for impacts.
While superstorms on the scale of the Carrington event might be rare, even smaller scale space weather can have a big impact. And when it strikes, every sector must scramble to react. Satellite operators may place spacecraft into safe modes or boost their orbits to combat increased drag. Airlines may be forced to ground flights while diverting other planes to avoid radiation. Power grid operators face split-second decisions and backup generation must be standing by. But every response plan relies on one factor: early warning. So do you mind if I geek out a little bit here and ask what's going on the screen here?
So what we have here is the sunspot region, and our first indication that we might be getting space weather typically originates from sunspots. We can run it through time and see if it's growing, decaying, that sort of thing. What we can also do is look at the magnetic field of the sunspot as well. And typically when we have those opposing magnetic fields all tangled up, there's a lot of energy that's stored there. So there's the potential for that energy to be released as solar flares and coronal mass ejections.
Where do you get all of your data from?
A lot of our data that we use for observations is satellite data. So if we look on the screens up here, we've got coronagraph imagery. So this is from a satellite which is 1 million miles away from Earth. And the center circle that you can see in both these images is a shield over the camera lens to block out much of the light from the sun. So all we can see is the outer layer, the sun's corona, hence coronagraph. And from that, we can see whether we've got these coronal mass ejections, these plasma bubbles leaving the sun. And the other images are looking at the sun in different wavelengths. And by doing this, you can pick out different features on the sun.
If there was going to be a big extreme event, what signs are you looking out for?
We would probably see a pretty significant solar flare, and then we'd be looking on the satellite imagery for that coronal mass ejection leaving the sun.
And can you really accurately pinpoint what particular areas might be most affected by it?
It isn't a local phenomena. It will affect like entire hemispheres. When we do meteorological forecasting, you've got thousands of observations on the ground. You've got loads of satellite imagery to feed into the models. When it comes to space weather, we're looking at a handful of satellites and limited ground observations. We can give a pretty good heads up that something big is coming, but we're definitely not at the level that we are at with meteorology.
Is there anything that you're excited about, like any new technologies that could help with predicting what's coming up?
It is a super exciting time in space weather if you're into space weather. There was a recent programme of work to deliver new monitoring capabilities. We've got models coming through from academia, from research institutes, which will really help us with our forecasting ability at the Met Office. The UK has been a key contributor to a satellite programme known as Vigil, and what it's going to do is it's going to give us a new side-on view of the sun. So when we see one of these coronal mass ejections leave the sun, we can really quickly see if it's headed towards Earth and get a better indication of the arrival time as well.
Institutions like the Met Office are making impressive strides in their forecasting. But there are still big gaps in our capabilities, gaps that new space missions, like Vigil, are hoping to fill.
Here at Imperial College London, a team of scientists and engineers are building vital instruments for the next generation of deep space satellites. Satellites whose gaze will be fixed firmly on the centre of the solar system.
Professor Jonathan Eastwood and his team are working on an ambitious new project that could be a step change in our ability to forecast space weather.
First question, what on earth is all of this?
So each of these boards, is a different part of the electronics of the Vigil magnetometer to measure the magnetic field in space. Vigil is this new space weather mission that is going to be launched to the L5 Lagrange point. So it's going to hang out in a stable gravitational point.
Lagrange points are sweet spots in space where the gravity of two massive bodies, like the Sun and the Earth, balance. Spacecraft can sit in these natural parking bays for years while using very little fuel to hold position. The James Webb Space Telescope, for instance, occupies the L2 point. L5 in the Sun-Earth system trails our planet by 60 degrees in its orbit, 150 million kilometers away in deep space.
What's so special about L5?
Because of the sun spinning. And so if you're at L5, what you see is stuff on the sun that a few days later will rotate into view of Earth. And so by going there, you can see what is developing on the sun's surface before you can see it from Earth.
So where are we now with space forecasting, and how much will it improve once you get Vigil to its station at L5?
Right. So the first part of Vigil's payload is the magnetograph looking at the surface and looking at the development of those sunspots. You're looking from around the side, that gives you a few more days where you can start to raise the flag and say, hey, something's brewing. The next bit of Vigil is then imaging things going from the sun to the Earth. And then the last bit we're looking at here is actually measuring the properties of the solar wind and its magnetic field itself, because that's really important for some particular types of space weather. But it also is just part of the data that you would use in the same way that you use all the data to make a regular weather forecast.
So it's almost like modelling. If you're understanding whether it's going to rain tomorrow, you need to know about the storms and clouds, but you also need to know the state of the atmosphere and, and the winds.
Exactly. And so you could imagine, you know, in 10 years, the forecaster will have the screen showing the front view from the Earth, and right next to it, there'll be another image from Vigil, and you'll be able to look and just have that longer baseline. The modelling and the imaging of the CMEs going towards the Earth, and you'll be ingesting data for your heliospheric model.
With its unique vantage point and capabilities, Vigil could transform the way we observe the sun and predict space weather.
Okay, so let's say I'm convinced that we need a magnetometer at L5 as part of this mission. What makes how do you design it? What makes a good magnetometer?
So we're coming from decades of heritage in sending stuff all over the solar system. But it is different from a science mission. So we want, within the measurement being made on the spacecraft, less than an hour later, it needs to be there in a state that a forecaster can use it. And also, it has to work through space weather events.
I don't think I've had a chat like this with somebody ever on my tablets going out, because you're very customer focused. You know, we've reached the point where this is something that's needed by the Met Office, by industry and so on. Tell me about that as a physicist. It's a very different way of thinking.
Yeah, space weather is very much applied because it's all driven by ultimately the socioeconomic impact. The thing that I spend a lot of time wondering about with Vigil is we're building it now in 2026. It's going to be operating in 2036. And well, what is space going to look like in 2036? What is our everyday life going to be like? We rely on space technologies in so many ways. As we use space more, we are therefore more exposed to space weather, and therefore there is a need to be on top of it.
Well, it seems to be a boom time for space weather, and space weather missions in particular. What's changed that's led to this attention?
I think it's just a realization that if there was a really big event of the order of a Carrington event, then that could have a really severe impact.
There's also a story about complexity as well. I think in understanding and getting better at predicting weather on Earth, I think people have realized the complexity of the system that we're trying to predict.
The complexity with space weather is that it's not one single impact. It can impact on power grids through one particular type of physical interaction. It can impact on position, navigation, and timing with a totally different type of physical interaction. And it can damage electronics on satellites and so on through another totally different type of physical interaction. All of those things could happen at the same time or at different times in different regions of the Earth in different ways. And that provides a huge amount of complexity, because suppose that you have a power outage and you also don't have positioning, or it interferes with communications. And it's not made easier by the fact that, of course, a really, really severe event is, we talk of the order of 1 in 100 years. But that means the return time will be something we're likely to experience, in the next few decades.
We'll come back once Vigil's on site and look at the data coming in. Jonathan, thank you very much.
You're very welcome.
Daring new missions like Vigil could revolutionise both our understanding of space weather and our resilience to it. But as Pete can show us, there are plenty of ways to admire the sun's raw power right from your own backyard.
With more hours of sunshine, the early summer is a great time to observe our nearest and dearest star. But first, a warning. You should never look directly at the sun without adequate protection. So what you'll need is a pair of these, which are eclipse glasses. And what you need to look for is a mark which indicates the International Organization of Standards, or ISO mark. The specific number is 12312-2. These will block out 99.999% of visible light, all ultraviolet and infrared. But even with these, you shouldn't look at the sun for a prolonged period of time. Okay, so now we're safely protected, what can we see?
Sunspots are dark patches visible on the sun's surface, cooler areas caused by intense magnetic fields. Each can last for between a few days and up to several weeks. Large sunspots or sunspot groups may be visible without a telescope if you have sharp eyesight, but again, you'll need to be looking through a certified filter to try.
For those with telescopes, eclipse glasses aren't enough. Here you'll need a white light filter to protect your eyesight and your equipment. Now these can be purchased ready-made like this, or you can make your own with a bit of DIY skills, certified solar film, cardboard and some sticky tape. You need to make sure it hasn't got any defects, so hold it up to the sun, just make sure there are no tears or rips or pinprick holes in it. If you find any of these, you need to discard the filter and get a new one.
With a telescope and a white light filter, you should be able to see granulation on the sun's surface known as the photosphere. This textured appearance is caused by cells of hot plasma rising from the star's interior. And with an H-alpha filter, you'll be able to see details of the sun's chromosphere. The chromosphere is the second main layer of the sun's atmosphere. If you're lucky, you may be able to spot a solar flare, or more commonly, a prominence. They are sometimes the precursors to coronal mass ejections, the explosions of matter that can cause the northern lights.
Why not try some of these techniques yourself? You could even try taking a photograph of the sun through your telescope. If you get something, you could send it to our Flickr account, details of which can be found at bbc.co.uk/Sky at Night.
Space weather can be pretty scary stuff, but it doesn't have to be a disaster movie. Our knowledge of space weather is evolving rapidly, and with experts across the world looking at the skies for danger, I think we're in safe hands. Good night.